Thank you for taking interest in my research titled Implementation of a Low-Cost, Low-Pass Filter Using Microstrip Structure. I'm Rena Viele and I worked with Dr. Shantanu Chakraborty at Valdosta State University. Starting off, a low-pass filter is a filter that impedes high frequencies while allowing low frequencies to pass. Low-pass filters are commonly used, for example, in the tone knob of an electric guitar, in synthesizers, and to remove high-frequency noise from a circuit. My goal was to design and implement a low-cost, low-pass filter using a microstrip structure. Microstrip structure was used because of its compactness and easy-to-implement planar structure using printed circuit board or PCB. The ground plane of the filter consists of a copper layer. Next is the dielectric layer that was constructed using PCB or FR4 board, which has a dielectric constant of 4.4, and the top layer is the transmission layer, which is made up of copper tape pieces, which have a thickness of 1.5 millimeter and will soldered together. These materials were selected for their low cost and commercial availability. I have tested the frequency response of the low-pass filter from 100 kHz to 5 GHz using a vector network analyzer, which can act as both signal generator and receiver. I have collected the S21 or transmission parameter data, which is a measure of the signal coming out from the filter or port 2 relative to the signal entering the filter from port 1. The experimental S21 parameter data was then compared to the simulated S21 data. I've created a model of my filter using a free EM simulator named Sonnet Lite. My experimental values of the transmission coefficient S21 rolled off much faster compared to the Sonnet model between 100 kHz to 1 GHz. We have found some oscillations between approximately 2 GHz and 5 GHz in the experimental data that is not present in the simulation result. My experimental filter did impede the transmission of higher frequencies above 1 GHz. At 1 GHz, the S21 value is negative 1.80 decibel, while at 3 GHz, the S21 value is negative 8.61 decibel. For comparison, the Sonnet model shows us S21 value of negative 0.72 decibel at 1 GHz and S21 value of negative 13.12 decibel at 3 GHz. The cutoff frequency at negative 3 decibel occurs at 1.88 GHz for the experimental filter and at 1.49 GHz for the Sonnet model. To conclude, my experimental filter does function as a low-pass filter at sub-gigahertz frequencies. The filter's performance can be improved by using higher precision tools to cut the FR4 board and the copper tape, and using conductive silver paste to ensure a good connection between the different pieces of copper tape forming the transmission line instead of soldering.